So we have a test to see when a function is differentiable, and it comes in the form of this theorem. And it's fairly straightforward. All we need to do to check whether or not a function is continuous at a given point a, b, is to compute the partial derivatives and evaluate them at a, b. Well, not evaluate them, but check to see that the partial derivatives are continuous near that point. So in other words, continuous on some little disk centered at a, b, or little rectangle. And then that'll be enough to give us that f is differentiable at that particular point. So let's look at an example of this. We'll take the function x e to the xy, and I'm going to be tasked with doing a couple things. First, I'm going to show f is differentiable. And then for that, whoops, I just moved part of that. Show it's differentiable. And so then for that, we'll use this handy theorem, which will give it to us. And then for the second part, we will estimate the value of f at some location 1.1 minus 0.1. Okay, and so the idea here is that once it's differentiable, then we know from the previous clip that we can estimate this using the differential. So that's the idea. And then the other thing that you should think whenever you see a question of this form, so like estimate the value at some point, is that you look at this point 1.1 and minus 0.1, and the idea is this is close to some location where it's easy to compute things, namely 1, 0. So we're going to be using the linear approximation based at 1, 0. So this is going to be our location for tangent plane. And so that's where we'll be using the differential. Okay, so let's go do part 1. So part 1, by the theorem, we just need to check the partial derivatives. So if we look at the partial of f with respect to x, then let's see. So product rule is going to give us, when we differentiate with respect to x, if we put the derivative on the x, then we just get the exponential. And if we put the derivative on the exponential, then we have x times, and we're differentiating with respect to x, so it's going to kick out a copy of y, e to the xy. And then I guess if you want, you could factor that as 1 plus xy, but that's not strictly speaking necessary. We also compute the partial with respect to y, and in this case there is no product rule because x times the exponential, well, x doesn't contain any y's, so it's constant, so the x is constant with respect to y. So then we just treat the x out in front like a constant and differentiate the exponential, and it kicks out a factor of x, and so now we have two factors of x out front, and we have a partial x squared e to the xy. Okay, so these functions are products of polynomials, polynomials times exponential functions. And so polynomials are continuous and exponentials are continuous, and the product of continuous functions are continuous. So these guys are all very continuous functions. Okay, so we have, we conclude, so fx, fy are continuous everywhere. So f is differentiable everywhere they're continuous, which is everywhere. Okay, now for part 2, we use the differential at 1, 0. So let's see. So fxy is going to be given by, and then we've got f of 1, 0 plus fx 1, 0 x minus 1 plus fy 1, 0 y minus 0. All right, so I'm just plugging in the points that we're looking at. And then this is, let's see. So if we evaluate f at 1, 0, then we've got 1 times e to the 0, which is just 1. And then we have the x derivative, which we found in the previous step. And so if we evaluate 1 plus xy e to the xy at this location, what's going to happen? So this is going to be equal to 0, and this is going to be equal to 0. So we have 1 times e to the 0, which is 1. So we get 1 times x minus 1. And then for the y derivative, let's see, some similar computation is going to have, so we're going to have 1 squared e to the 0, which is 1. And then that's times y minus 0. And so doing the arithmetic, we have, let's see, x plus y. All right. So now if we look at 1.1 minus 0.1, then let's see. So then we have that this guy is approximately equal to the sum of its arguments. So 1. Okay, and so that is our answer. That is our approximate value for f at this particular point. In actual fact, the value, if you calculate this with a calculator or computer, you get 1.1 times e to the negative 0.11, which works out to 0.98542 ... So pretty good.